Hey guys, this video is for Mount San Antonio College Chem 10 students. This is some practice for your problem set on lecture 14, which covers your gas laws. Reminder, your four properties of gas are pressure, temperature, volume, and moles. Temperature you're going to measure in Kelvin. You might sometimes see it in Celsius or Fahrenheit when it's given to you, but your calculations must be in Kelvin unless otherwise specified. And same thing for moles. You may be given the information in grams, but you're going to need to convert that over to moles. All right, so let's check out our first question, which asks us to calculate the final pressure in atmospheres when a gas with an initial pressure of 1.00 atm at 25 degrees Celsius is cooled to negative 12 degrees Celsius. The number of moles and volume are constant. So if you refer back to your gas laws, you will see that the gas law that relates temperature and pressure is going to be Gay-Lussac's law, which tells us the temperature and pressure are directly related. And the formula that we're going to use for that is T1 over P1 equals T2 over P2. And you can also use the inverse depending on what it's asking you for in your equation. So let's go ahead and get our values here. Our P1 is going to be our initial pressure, which is 1.00 atm. And our T1 is 25 degrees Celsius. That's what we're starting out with. And remember, it needs to be in Kelvin. So we add 273 to convert that to Kelvin, which gives us 298 Kelvin. Our P2, our final pressure, is actually what they're asking us for. So that's going to be what we're solving for in our equation. And our final temperature is negative 12 degrees Celsius. Same thing there, add 273, and that gives us 261 Kelvin. Our formula that we're going to be using is P1 over T1 equals P2 over T2. We're solving for P2, so we need to get that by itself. We can do that by cross-multiplying over here and get rid of that T2, and then we would need to do the same thing on the opposite side. So our final formula is going to be P2 is equal to T2 times P1 over T1. All right, let's plug everything in. Okay, our first one is T2, which was 261 Kelvin, times P1, which was 1.00 atm, and that's over T1, which was 298 Kelvin. You can cancel out your kelvins, which leaves you with atm, which makes sense because we're solving for pressure. And if you work that out on your calculator, your answer should be 0.875 atm. Remember your sig figs. And there you go. All right, next one. Calculate the final temperature in Fahrenheit when a sample of air at 75 degrees Fahrenheit and 745 mmHg is heated to give a pressure of 982 mmHg. The number of moles and volume are constant. So here again, we're relating temperature and pressure, so we can use Gay-Lussac's law again. And this time it looks like we're going to be solving for temperature. So we're going to use the inverse on Gay-Lussac's law, which is this formula right here, because that just makes it a little bit easier in the calculations. So let's go ahead and plug this in. Or excuse me, get our values. P1 is our initial pressure, which is 745 mmHg. Our T1 is 75 degrees Fahrenheit. Now remember, it's asking for the temperature in Fahrenheit, so we don't need to convert that to Kelvin. We're okay there. Okay, our final pressure is 982 mmHg, and our final temperature again is what we're solving for. Our formula that we're going to use is going to be T1 over P1. We're using the inverse this time, and T2 over P2. We're solving for T2, so we're going to get rid of P2 by cross multiplying again, just like we did before. Need to do the same thing on this opposite side, and our final formula is T2, which is equal to P2 times T1 over P1. Plugging everything in, T2 is equal to P2, which is 982 mmHg, times T1, which was 75 degrees Fahrenheit, and that's going to go over P1, which is 745 mmHg. Cross those guys out, you're left with 75 Fahrenheit, which is what you're solving for, Fahrenheit. If you plug it in, you are going to get 98.859 degrees Fahrenheit is what I got, and which gives you 99 degrees Fahrenheit. Final answer. All right. Sparkling wine are bottled at 6.00 ATM. There is usually about 12 milliliters of gas at a temperature of 25 degrees Celsius. What is the final pressure of the gas in ATM when the volume and temperature changes to 9.0 milliliters and 75 degrees Celsius, respectively? All right, so here we've got a lot of things changing, and the only thing that looks like is going to stay consistent that our problem doesn't talk about is the amount of the gas, meaning the moles of gas. So our N is going to stay constant. Now we know if we look at our gas laws that our combined gas law is what we need to use when everything is changing, pressure, volume, and temperature, but moles of gas do not change, they stay constant. So our formula that it gives us is P1 times V1 over T1, which is equal to P2 times V2 over T2. Let's come back here and find our values. So our P1 is our beginning pressure, which is 6.00 ATM. Our T1 is our initial temperature, which is 25 degrees Celsius. We do need to convert that into Kelvin because it's not otherwise specified, which gives us 298 Kelvin. And our V1 is 12 milliliters. Our P2 is, what is the final pressure? So that's what we're solving for. And our T2 is temperature changes to 75 degrees Celsius. Convert that to Kelvin. And lastly is our V2, which is our final volume. Volume changes to 9.0 mLs. Okay. Our formula is P1 V1 over T1 is equal to P2 V2 over T2. All right, what are we solving for? We are solving for P2, so we need to get this guy by himself. The first thing we can do is cross multiply T2. We're going to do that same thing on this side, and then we can divide by V2 to get rid of this guy. Need to do the same thing on the other side. So our final formula is going to be P2 is equal to T2 times P1 times V1 over V2 times T1. Let's plug everything in. Okay, so we've got P2 is equal to 348 Kelvin times our P1, which is 6.00 ATM, and our V1, which is 12 milliliters, all over V2, which is 9.0 mLs, times our T1, which was 298 Kelvin. Cross out all your guys that are alike there. And if you plug all of that in, you are going to get 9.34. So pay attention to your sig figs. You've got 2 sig figs, so your final answer is going to be 9.3 ATM. Check it, you know you're solving for final pressure. You've got pressure in ATMs, so you're good. A sample containing 9.4 grams of H2 gas has an initial volume of 19.0 liters. What is the final volume in liters when an additional 3.00 moles of AR gas is added to the container? All right, so here we are relating volume and moles, which is V and N. If you go back to your laws and see which one relates those two, you should come up with Avogadro's law, which tells us that the volume of gas is directly related to the number of moles of gas. And our formula is N1 over V1 equals N2 over V2, and you can use the inverse of that as well, and that is when temperature and pressure do not change. Okay, so let's go ahead and find our values here. So our initial volume that we're starting out with is 19.0 liters, and our initial quantity of gas in moles is actually, we're given grams, 9.40 grams, so we're going to need to convert that to moles. Okay, so in order to convert from grams to moles, we need to find the molar mass of this. This is H2, which means we have 2 hydrogens. The molar mass of hydrogen is 1.008, I believe, times 2, which gives us 2.016 grams. That's our molar mass. So then you're going to go over and convert it. So we've got 9.40 grams of H2, and you'll need to do a conversion factor for that. I need to put my molar mass of grams on the bottom because I want this to cross cancel out. H2 in every 1 mole. Okay, so these guys are going to cross cancel out, and your answer that you're going to get is 4.66 moles of H2. So that's going to be your N1, your initial value. Okay, and our V2, our final volume, looks like that's what we're solving for, so we don't know that yet. Our N2, okay, so this is actually a little bit tricky. A lot of students make this mistake, including myself the first time around, because you get in a hurry when you're going through it and you don't really pay attention sometimes. So it's telling us you might just want to plug in 3 moles right here, but actually what you're doing is you're adding 3 moles of gas to the container. It says when an additional 3 moles of gas is added to the container. So you're really adding 3 moles to what you already have. Okay, so that's kind of the tricky part. So instead of 3 moles, you're actually getting, you have 7.66 moles, right? Because that's 3 plus 4.66. So that's going to be your N2. All right, now our formula for Avogadro's law is V1 over N1 is equal to V2 over N2. And we are solving for V2, so we need to get that by itself. Let's go ahead and cross multiply over here, get rid of that. Do the same thing to the other side. And your formula that you're going to use is going to be V2 is equal to N2 times V1 over N1. Let's plug everything in. V2 and our N2 is 7.66 moles times V1, which is 19.0 liters, over N1, which is 4.66 moles of H2. There. These can cross multiply, or excuse me, just cross out, and you're ending up with liters, which is great because that's what we're solving for. And once you put that into your calculator, the answer that you get should be 31.23 liters. Okay. In a gas mixture, the partial pressures are argon 383 torr, neon 72 torr, and nitrogen 205 torr. What is the total pressure in torr exerted by the gas mixture? Okay, so here you've got just a bunch of partial pressures that make up a gas mixture. So if you go back to your laws for this one, you have Dalton's law of partial pressures, which basically says that when gases are a mixture and each component behaves in the same manner, your formula is going to be P total. It's basically the sum of all your partial pressures. So P total is equal to P1, P2, P3, and etc. all added together. So we can go in here and let's write down what we have. So we've got argon, which is 383 torr. And then we've got neon, which is 72 torr. And nitrogen, which is 205 torr. And basically what you're going to do is you're going to add all those up, and what you should get is 660 torr. And you're good to go. All right, the second part of the question says, if helium gas is added into the mixture, resulting in a total pressure of 1.00 atm, what is the partial pressure in torr of the added gas? So what you need to do is you're just basically converting atm and torr. 1 atm is equal to 760 torr. So basically what you're doing is you're adding in 1 atm, and you can do a conversion factor if you want, or you can just write it out. Okay, so I'm given 1.00 atm. And I know that for every 1.00 atm, I have 760 torr. Cross cancel these guys, and you get 760 torr. That's your partial pressure of the added gas. All right, consider the scenario below. And actually, sorry, I had to put my scenario over here on the side. So this is our scenario here. Okay, what property of gas is depicted as being changed in circle 1? Okay, so if you look at the circles, it's gotten smaller. So basically you have a choice. Did we change the pressure of the gas? Did we change the volume of the gas? Did we change the number of the gas molecules? Or did we change, moles, or did we change the temperature? So we basically changed the size. If we count the gas molecules inside, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Those stayed the same, so we didn't change N. We don't know if we changed the temperature, it doesn't say, but pressure and volume are directly related. So it looks like we changed the volume here, we made it smaller. So what property of gas would change due to the change mentioned above? Okay, well, like we said before, volume and pressure are directly related. So if we decrease the volume of the container that our gas is in, the pressure is going to increase. And the law actually that we can go back, and I said directly related earlier. I meant to say that they are inversely related. And the law that we look at for that is Boyle's law, which tells us that volume is inversely related to pressure. When the volume increases, pressure decreases. When volume decreases, which is our situation that we have, the pressure will increase. So if we go back here and look at our picture, our volume did decrease. So that means that our pressure is going to increase. Okay, so that's going to affect our pressure. It's going to increase. How will it change, up or down? All right, well, we just said that our pressure is going to increase, so it's going to go up. And which law will help you decide that? And that's the one that we just checked out, which was Boyle's law. Again, volume inversely related to pressure. Volume decreases, pressure increases. Can you explain your answer using kinetic molecular theory? Well, as you would know from your lecture, according to kinetic molecular theory, molecules are bouncing around, gas molecules are bouncing around inside their container. They're bouncing around, they're colliding with each other, they're hitting each other. It causes them to change in direction every time that they hit against each other. And that causes pressure because they're hitting against the walls of the container, causing greater pressure. So if the volume is reduced, if that space that they're in is smaller, they have less space to move around, right? So that means that they're going to collide with each other and hit each other more often because they have less space to move, which means they're going to hit against the walls of the container a lot more, which is going to cause more pressure. And I'm not going to write that out because that's really long, but that's basically what that one is asking us. The next one is, now imagine starting at state 2. You cooled this gas down, but you kept the same volume as state 2. How would the pressure in this new state compare to the pressure in state 2? It's going to be lower because your volume is the same, but you decreased the temperature. So we also know that increasing temperature causes an increase in pressure because of the kinetic molecular theory. Increase in temperature causes the gas to move around more frequently as well. So if you're cooling it down, then the molecules are going to move around slower. They're not going to collide against each other as much. Therefore, they're not hitting the walls of the container as much, which is going to decrease the pressure. So we can answer that one and say that it's going to be lower. Again, explain this using kinetic molecular theory, which is what we just talked about. So An increase in temperature for heat causes more kinetic energy. A decrease in temperature will result in less kinetic energy, less bouncing, less collisions, less hitting of the walls of the container, results in less pressure. Okay, so hopefully that helps you guys out a little bit on your problem sets and explains it a little bit. Thanks so much for listening.